Welcome to another episode of Learning. Please like my videos and share them with your friends and colleagues. Please join as a member in my channel and support me and my channel. Please subscribe my channel if you have not already subscribed. Thank you. Right, we continue the discussion of the solutions of the problems from the question paper CSIR National Eligibility Test held in the month of March 2025. It is a rescheduled examination for Assam Center. In this video, we discuss the solution of a problem from the section Linear Algebra, and the problem is related to the symmetric bilinear form. This question is placed in part C, which is a multiple select question. There may be more than one answer and the question carries 4.75 marks. The question ID is 706558. Further, this question is suitable for all these examinations. Right. The given question is, let V be a two-dimensional real vector space with a basis, the set consisting of V1, V2. V is a vector space over the field of real numbers and its dimension is 2, and a basis for that is given to be V1, V2. Let F be a map from V cross V to R be a symmetric bilinear form. You know what is the meaning of symmetric bilinear form? Let R is equal to F of V1, V1. S is equal to F of V1, V2. T is equal to F of V2, V2. Which of the following statements are necessarily true? We are given four options. Option 1, F of V2, V1 is equal to minus S. Option 2, if R is equal to S is equal to T, then either F of V, V greater than or equal to 0 for all V belongs to V, or F of V, V is less than or equal to 0 for all V belongs to V. Option 3, if F is positive definite, then R not equal to S, S not equal to T, and R not equal to T. Option 4, if F is positive definite, then F of V1, V2 is 0. Right. Let's now discuss the solution of the problem in detail. We are given V is a vector space over the field of real numbers, and it is given its dimension to be 2. And B is equal to the set consisting of V1, V2 is a basis of V. Right. We are given F from V cross V to R is a symmetric bilinear form. That is, F satisfies linearity in each argument. Right. Now, we have R is equal to F of V1, V1, S is equal to F of V1, V2, T is equal to F of V2, V2. Those of you who are not familiar with the definition of the bilinear forms, get back to the book and find out what are the properties. Right. Now, S is equal to F of V1, V2 is equal to F of V2, V1. Why? Because F is symmetric. Right. Now, we call on option 1. F of V2, V1 is equal to minus S. If this is true, then it contradicts the symmetry of F unless S is equal to 0. Therefore, option 1 is not true. Agreed. We continue in the next slide. Right. So, corresponding to every bilinear form, we associate a matrix A. Now, the matrix A of V with respect to a given basis. Let capital A be the matrix of the bilinear form with respect to the given basis, and that is given to be a 2 by 2 matrix F of V1 comma V1, F of V1 comma V2, first row, F of V2 comma V1, and F of V2 comma V2, second row. That is a 2 by 2 matrix R S S T. Agreed. The dimension is 2, therefore we get a 2 by 2 matrix. Right. Now let U V be any two elements of V. Since B is equal to V1 comma V2 is a basis, U is a linear combination of V1 V2, V is a linear combination of V1 V2. So U is equal to alpha U1 plus beta V2, where alpha beta are scalars coming from R. V is equal to alpha V1 plus beta B V2, B times V2, where A and B are scalars coming from R. Then F of U comma V is equal to X transpose multiplied by A into Y, where X is the column vector alpha beta. What is this column vector alpha beta? It is the coordinate vector of U. And what is the coordinate vector of V? It is AB, column vector AB. Y is equal to AB. See, be careful. F of U comma V and U and V are any two vectors. They are to be written as a linear combination of these basis vectors, and from that linear combination you have to write down their that vector X as alpha beta column vector alpha beta, that is coordinate vector of U, coordinate vector of V AB. So that's what you have to write. Now suppose let V be any element of V, and V is AV1 plus BV2, AB belongs to R, then X is the coordinate vector AB, this is a column vector, then F of V comma V will be X transpose multiplied by A into X. So what is this? X transpose AX. What is this? It's very familiar to you. It is a quadratic form. F of V comma V is X transpose AX is a quadratic form in two variables, and A is its matrix of the quadratic form. Now note that F is positive definite because it is a quadratic form. You can talk about positive definiteness. That is if and only if the associated matrix A, that is RSST, is positive definite. It is if and only if. Right. We are ready. Because your options given in 2, 3, 4, they talk about the positive definiteness. Right. So this is what we have. Option 2. If R is equal to S is equal to T, then either F of V comma V greater than or equal to 0 for all V belongs to V, or F of V comma V is less than or equal to for all V belongs to V. Now you see F of V comma V. V comma V is a quadratic form. Greater than or equal to 0 for all V belongs to V means what? It is a positive semi-definite. and f of v comma v is less than or equal to 0 for all v belongs to v is negative semi-definite. That's what it says. So anyway, now let R is equal to S is equal to T. Then the matrix A will be R S S T will become R R R R. Is a matrix of the quadratic form f of v comma v. Now study the eigenvalues of A. The eigenvalues of A. You see, this is a singular matrix. Its determinant is 0. Therefore, 0 is an eigenvalue and its trace is 2r. 2r is the sum of the eigenvalues. So, 0 plus another eigenvalue is equal to 2r. Therefore, the other eigenvalue is 2r. So, now the eigenvalues of A are 0, 2r because A is singular and the trace of A is 2r. Right. And if the eigenvalues of A are 0, 2r and if r is positive, then what will be A? What will be A? If R is positive, then A is positive semi-definite. In terms of the matrix, what you are talking about, the eigenvalues are 0, 2r. So in these eigenvalues, all are positive and one of them is 0. Then you will get a positive semi-definite matrix. If R greater than 0, then A is positive semi-definite. When A is positive definite, semi-definite, the same thing will happen to the quadratic form f of v comma v. Therefore, the quadratic form f of v comma v is greater than or equal to 0 for all v belongs to v. Positive semi-definite definition is greater than or equal to 0 for all v belongs to v. If R is negative, then A is negative semi-definite because the eigenvalues are negative and one of them is 0. Then A will be negative semi-definite. Then the underlying, the corresponding quadratic form will be negative semi-definite. The quadratic form f v comma v is less than or equal to 0 for all v belongs to v. Thus your option 2 is true. Right. We continue in the next slide. Right. Option 3. If f is positive definite, then r not equal to s, s not equal to t, and r not equal to t. So it says whenever f is positive, semi-positive definite, then this will happen. And the fourth option is whenever f is positive definite, then f of v1 comma v2 must be equal to 0. This is what it says. Is it true? That's the question. So we will give a count and we recall f is positive definite because this is a positive definite if and only if the associated matrix A RSST is positive definite. This is not true. For that we construct a counter example. Consider the standard inner product on R square with basis vectors v1 is 1, 0 and v2 is 1, 1. It's very clear. One is not the multiple of the other. They are linearly independent and hence it's of dimension 2. Therefore, it forms a basis. And we take the standard inner product. That means v comma u is v dot u dot product. Standard inner product we take and that forms a bilinear form. Right. Then R is equal to f of v1 comma v1 is the inner product of v1 comma v1, v1 with v1, that is 1, 0 with 1, 0, that is 1 into 1 plus 0 into 0 is equal to 1. It is standard inner product is this one, the dot product. And S is equal to f of v1 comma v2, that is the inner product of v1 with v2, that is the inner product of 1 comma 0 with 1 comma 1, that is 1 comma 1 plus 0 comma 1 is equal to 1. And T is f of v2 comma v2, that is 1 comma 1 with 1 comma 1, that is 1 into 1 plus 1 into 1, that is 2. Therefore, the associated matrix A will be RSST, that is 1, 1, 1, 2. Agreed. And clearly A is positive definite. How can you say? how can you say? All its leading minors. 1 minor is 1 positive. 2 minor leading 2 minor is determinant is 2 minus 1 positive. So all its leading minors are positive, therefore it's positive definite. Therefore the corresponding bilinear form is positive definite. So F is positive definite. Here, do you see R is R? What do you see? R is equal to yes. Is S is equal to T? No. Is R is equal to T? Is R is equal to T? No. Note that S is not equal to T. R is not equal to T. But R is equal to S. So we are not getting this R not equal to S, S not equal to T, and R not equal to T. Not necessary. Not necessary. So the strict inequality R not equal to S is not necessary. So this option 3 says whenever F is positive definite, this must happen. But this is not happening. Therefore, option 3 is not true. And whenever F is positive semi-definite, in option 4, F of V1 comma V2 must be 0. That means S must be 0. Is S 0 in this? No, S is 1. So we have S is F of V1 comma V2 is 1, not equal to 0. But F is positive definite. Therefore, the option 4 is also not true. Summarizing all the options, the answer to this question is option 2. That is the detailed discussion of the solution of the given problem from the section linear algebra, which is related to the concepts and results related to symmetric bilinear forms. And those of you who are not familiar with symmetric bilinear forms, make a small notes about it. And as far as this lecture is concerned, I made it very simplified and self-contained, except the definitions and all that. Right? I am sure that you have understood the solution of this problem. Thank you for watching this video now. Please like my videos and share them with your friends and colleagues. Please join in my channel as a member and support me and my channel. Please subscribe my channel if you have not already subscribed. Yes. I'm sure that I'm going to meet you all once again in another episode of learning. Enjoy learning mathematics. I wish you all the best. Thank you.